Hello, it's Arkasha from MCAT Simplified. Today, we're going to do examples of Sn1, Sn2, E1, and E2 reactions. And with each of these examples, we're going to try to figure out, what is the most likely reaction pathway based on the substrate, the nucleophile/base, and the solvent. Okay, and we're going to try to figure out what product or products are going to be formed and which ones are the major ones. So let's start with number one. So we have this molecule here, and clearly there's a carbon right here. It's a tertiary carbon, right? 3 carbon groups attached to it, and then this chloride molecule. And then it's reacting with this molecule with the sulfur, okay? Sulfur group attached to a methyl group, and then it's as a salt, okay? So when it goes into solution, it's clearly in an H2O, so water solution, aqueous solution. It's going to dissociate, it seems like, to form, the sodium ion, the cation, and then the anion. Now, as it turns out, this species here is a very strong nucleophile. Okay, when it goes into solution, this whole thing is going to form Na plus SCH3. Okay, it has some lone pairs. It's a very strong nucleophile and actually a very poor base, as it turns out. But the issue here, right, is that this is going to be a tertiary carbon with this chloride bound to it. The chloride is the leaving group here. And we know that this species can form a very stable carbocation, all right, because it's going to be a tertiary carbocation. So and the other issue is that this cannot act, if we consider the Sn2 pathway, this isn't really able to go in there and just knock off that chloride because, again, there's a lot of steric hindrance from these carbon groups, okay? And so Sn2 is really not a possibility. It doesn't happen with tertiary carbons. And then E1 and E2 aren't possibilities because this is a very weak base, okay? It's only a really strong nucleophile. So what's going to happen is Sn1, where we're going to get a tertiary carbocation, right? The leaving group's going to leave. Chloride's going to leave on its own in that first step, the rate determining step. It's going to get a stable carbocation, and this is going to attack it and form, right? It's going to form the substituted molecule. All right. Now this, the carbon isn't chiral, but if it was, we would get a racemic mixture of RNS, optical isomers, okay? So this one is going to be Sn1. So Sn1 was the pathway. Notice the solvent is water. Again, usually these reactions are going to be in polar protic solvents, and that's a polar protic solvent, okay? So that's Sn1. It's really going to just produce that one product. All right, now this reaction here. So here we have this, this aromatic ring, this benzene ring, then this hydrocarbon chain, two carbons here and here, and then the leaving group, which is bromide, clearly the leaving group. And then it's in alcohol. And then we have this, what is this? KO-T-butyl. So this is actually basically tert-butyl alkoxide, okay? Because this is going to dissociate into potassium and then the tert-butoxide, okay? Which is essentially this, it's this molecule here. So notice, right, there's a carbon here, carbon here, carbon here, carbon here, and then this is full negative charge, okay, full negative charge right here. And this, of course, is very bulky. That's the first thing we notice. So when we see really bulky species, we're thinking less substitution, probably more elimination, all right? And then the other thing is we have the substrate. And the substrate, the leaving group, when this leaves, this is going to form a primary carbon, okay? It's on a primary carbon, rather. So if this left, and it was an Sn1 reaction, it would be a primary carbocation, which is extremely unstable. So Sn1 is most likely not going to happen, okay? But so really it's going to be between Sn2 and then its main competitor, which is E2, right? E1's not going to happen because, again, it proceeds through a carbocation. This is a primary carbocation if that bromide leaves. So it's really between Sn2 and E2. And so the deciding factor, I think, for the dominant product here is going to be the fact that this molecule, which can be either a nucleophile or a base, is really bulky. So even though this is primary, the fact that this base this nucleophile / base is really bulky, it's probably going to be mostly abstracting the adjacent hydrogen, okay, as the bromide leaves, and a double bond forms. So it's going to primarily go through the E2 pathway, okay, the E2 pathway. So we can draw the most likely product here with that, which is where we're going to have this this ring. Just going to draw that. And then, you know, the two carbons, always want to make sure we're counting out carbons. And then the bromide has left this carbon here. And so a hydrogen has been abstracted here by this base. So we're going to have a double bond between these two carbons. Okay. And this is going to be the E2 product. Okay. And so most likely, given just the facts of the situation, this is going to be the dominant product. Okay. Most likely. Now, the thing is that this is still going to be a primary carbon. So even with a bulky base, primary carbons are just very conducive to Sn2. So you will have actually some appreciable amount of Sn2 product, which in this case would probably look something like, I'm going to have to make this a little small, right? It's going to look something like this, where this oxygen is going to be attached. Okay. But definitely this is going to be the minor product, I think, in this case. And this is going to be the major product. All right. And again, there's no really big consideration. There's no consideration for stereochemistry here. Remember, there's always an inversion of configuration at chiral carbons with Sn2, but this carbon is not chiral. So that's not really a big issue here. Okay. And so then we have this reaction, and this is an interesting one because it has this hydrocarbon chain, so attached to this fluorine molecule, okay? And it's reacting with, again, another one of these, right? Very powerful nucleophile, like we said, and DMSO, which is a polar aprotic solvent, DMSO. And they're asking us, what is the reaction? So this is kind of a trick question because remember that with leaving groups, here's a leaving group consideration. With halide leaving groups, right, we got to remember that iodide is better than bromide, which is better than chloride, which is much better actually than fluoride. And that's because you're always trying, with these leaving groups, you want to produce the weaker Lewis base. And this is the weakest Lewis base of all of these. And this is actually a pretty strong one. It's very electronegative, okay? And as it turns out, actually, fluoride is such a bad leaving group that this reaction just won't happen. There's really not going to be any product with this reaction. So be cognizant of that, because even though everything seems really set up for like a good Sn2 reaction, primary carbon, really strong nucleophile, polar aprotic solvent, the issue is that this leaving group just sucks. It's not going to happen. Okay, so no product. Next, we got this molecule. We got this carbon. It's actually, it looks like a secondary carbon with, really there's two potential leaving groups here, fluoride and bromide. But the issue is that, again, fluoride is just a really bad leaving group. It doesn't really want to leave. So bromide is the only legitimate option here. So that's what's going to be the leaving group. Okay. And if it leaves, if we went through a carbocation pathway, this would be a secondary carbocation because it's got this fluoride, it's got this carbon here, okay? But the main issue with that, though, is that fluoride is also very electron withdrawing, so that would actually destabilize the carbocation. It's actually very unlikely that this could go through any form of Sn1 or E1 reaction for that reason. Because, even if it was like a secondary carbocation, sure, that's possible. But then with the fluoride there, it's extremely electron withdrawing. It actually makes that carbocation even less stable if it's present. Okay, so that's not going to occur. So then we're only dealing with Sn2 or E2 possibilities. And again, the solvent here, acetone, is polar aprotic, which also facilitates those pathways. And then notice we have this delta sign here, okay? And so that's suggesting that there's heat being added. And remember, heat favors elimination reactions. So most likely E2 in this situation is going to be the dominant pathway. And so if E2 happened, right, that would involve bromide leaving, right, detaching, and then at the same time, right, the hydroxide ion here, and this is a strong base and a strong nucleophile, but it's a strong base also, it will take this hydrogen, right, and these electrons will go here to form a double bond, okay? And so the major product here is going to be this, right? It's going to be attached to the fluoride, right? But this is where we need to think about some stereochemistry, all right? Because look, there's a double bond here, and then there's this group that's attached to it, you know, this ethyl group kind of, and then it has the fluoride here, or the fluorine atom. And so notice that they're on the same side of this double bond here. So this is actually the cis, or the Z product. But remember that we could also have this product, where it's on the opposite side. They're on opposite sides of each other. And this is the E, the entgainen, or trans. And remember that with these elimination reactions, the entgainen product is favored, is energetically more stable. There's less steric hindrance between these groups. So this is going to be the major product, the entgainen one. All right. Now, of course, here, this is a secondary carbon. And so you could actually have some substitution as well, where this will come in and knock off the bromide, okay? And so that will also still be a reasonable product. Remember that here E2 is favored for sure, but this is still going to be a reasonable product where, you know, we can draw that the OH acts as a nucleophile in this case, and it binds here, okay? And remember that what happens with Sn2 reactions is an inversion of stereochemistry. So this is indeed a optically active, so it's a chiral carbon, okay? And here the fluorine atom is coming out of the page, and hydrogen is going away from us, out of the page. So remember that because this proceeds through an umbrella mechanism where it attacks from the back, it's called a backside attack, the hydroxide comes in and it basically inverts the stereochemistry in the product. So now the fluoride is going to be away from us and the hydrogen is towards us. Okay? So in that case, right, if we initially had one enantiomer like R, then this one would go to S. And we can actually figure that out because if we look and we try to figure out whether this is R and S, hydrogen is already conveniently pointing away from us. And F is the, well, bromide is actually the highest molecular valued group. So this would be going, you know, it would be, bromine would be number 1, fluorine would be number 2, and then this would be number 3. So we're going this way, okay? So this is going essentially counterclockwise. So it's going to be S. So this is S, right? And this is now R, of course, okay? This is now R. So there's a complete inversion of stereochemistry for the Sn2. Okay, so these are our products here. Okay, so question 5, we have this big molecule here. Okay, we see the iodine's got to be the leaving group of whatever ends up happening. And it's attached to a carbon that's a tertiary carbon. Okay, so since it's a tertiary carbon, we got to start thinking Sn1 or E1. Okay, and then also notice that it's happening with like methanol present. It's a weak nucleophile / base, and then water also. That's a solvent, but again, it's polar protic. It's if it does anything solvolysis related, again, it's weak. So again, it's got to be Sn1 and E1, and most likely they're going to both occur to some amount here. So we want to draw this, right? This is going to form this carbocation, right? Which is nice and stable since it's tertiary. Okay, so positively charged. And let's think about the E1 pathway first, right? What's going to happen? Well, this molecule, which, you know, it can act as a base, and then I guess water could do it too in this case. And notice, by the way, sorry, that there is heat applied. So heat is applied. So that is going to make the E1 more likely. All right, E1 more likely because the heat is applied. Remember, increasing temperature makes elimination pathways more likely. So you have this carbocation, and if we think about E1, we know that we want to create the more substituted alkene, especially if we have a smallish base. And again, this isn't some crazy bulky base where we have to worry about steric interactions and maybe the Hofmann product. In this case, we're definitely going to try to get the Zaitsev product, the more substituted alkene, as the major one. Notice that we want to identify the hydrogens that can be taken adjacent on carbons adjacent to the carbocation. So there's one here, right? There's going to be one here, and then there's one here. And notice that if we take this one here, then the double bond forms between these two carbons, and those carbons are the most substituted ones. So that's ideal. That's going to be the Zaitsev one. Okay. So this is what this is going to look like. Now you could also have some product where the double bond will form here, okay? And then you might have some product where it forms here. But those are going to be definitely more minor products, okay? This is going to be the most stable one. This is the Zaitsev. It's going to be the major one. And it's probably going to be the major product for this whole reaction because, again, the elimination pathway is going to occur more readily because of the heat. You can try to draw these other two products for practice, though. And then we will have some Sn1 reaction. So if we think about the Sn1 situation, you're going to have after the carbocation forms, this methanol will attack, okay, when it acts as a nucleophile. And you're going to get, right, you're going to get this where it still has that hydrogen. So now it's actually protonated. But then maybe water will come in and it's going to take this hydrogen, right? So then it will become deprotonated. And so you're going to have the final product, which is the Sn1 product. Okay. And notice that actually initially this whole thing was chiral because there's, it's basically 4 unique attachments. And because of that, right, this is going to be, there's going to be some R and some S because remember with the Sn1 reaction with the carbocation, it can approach from both sides pretty much equally. So you're going to have a racemic mixture of this product here. All right. But again, the major one is going to be the Zaitsev. The E1 and the Zaitsev specifically from the E1, the most substituted alkene. Okay. So then we have this reaction. So here, again, we have a leaving group on this big molecule and the carbon is tertiary. So we have to be thinking something along the lines of Sn1 or E1. And notice they have heat again, so we got to be thinking elimination. In this case, they have sodium ethoxide, so it's going to form a nucleophile or base in the form of this, basically. Okay. And right, this is a strong nucleophile, but it's not really going to go Sn2 or E2 because this is very substituted carbon. It's not going to occur in one concerted mechanism. All right. So primarily we're looking at E1, Sn1 again, but most likely E1 because of the heat. All right. So in this case, right, we're going to form the tertiary carbocation. Okay. And as this leaves. And then with the E1, right, this is going to take one of these hydrogens. It's not going to take this hydrogen because that's going to be a really minimally substituted double bond. Like that's going to be very, very minor if it's formed at all. It's going to take one of these two. It doesn't matter which one though, because this is a symmetric molecule. They're equivalent. So this is going to then form, right, the major product, the E1 product, and also what's the Zaitsev or more substituted alkene, this one here. E1 and Zaitsev. The other one that can form, but probably doesn't form in really any appreciable amount, is between this carbon and this carbon up here, which also has a hydrogen. but that is it's less substituted than this one. So this is going to be the major one. Now here you can still have some substitution. So if this attacks this alkoxide, because this is a strong nucleophile, remember, and if it's a stronger nucleophile, it makes the substitution chances, the amount of substitution that happens increase. So if substitution happens at this carbocation, then you're going to still have this methyl group attached, but now you're also going to have the nucleophile attached. Looks pretty funny like that, but I'll draw it like this, right? So that's going to be the Sn1 product, right? But because of the heat, the E1 is going to probably be the major one, and specifically the more substituted E1 product. All right, so number 7. So another ring, and then we have this OH group. So, this is the only plausible leaving group here, but we have to make it a good leaving group first. And it's attached to this carbon. So initially this carbon is actually a secondary carbon. And so here we might see, we might start thinking about some interesting situations occurring, because this is in a polar protic solvent, and instead of like a clear nucleophile or base, they're adding acid. So we didn't really talk about this in any of the videos, but what can happen is you can actually produce a better leaving group from like an alcohol by adding acid, which will then react with this and protonate it, okay? It will protonate it. So let's draw what that might look like. So we're gonna have this, and then this is attached, and this oxygen has been protonated by the strong acid, which is hydrochloric acid. And now it's positively charged. So what will happen is that this can now very readily leave, right? It can leave, and this will basically form it will form a carbocation intermediate. And we'll talk about why it's going to most likely form a carbocation intermediate here, right? It's going to be positively charged, and then we also produce water, because this is basically now a water leaving group, okay? So this is acid catalysis, because adding the acid makes this a very good leaving group, okay, because it'll react to it. But look, now we have a carbocation. It's a secondary carbocation, so not the most stable in the world. But notice that, and remember, whenever you have a carbocation, you want to start thinking, are there rearrangement possibilities? All the previous ones we talked about, they're already tertiary, so really there's no reason for rearrangement. But can we rearrange this in any way to create a more stable carbocation, like a tertiary one? Well, a tertiary one could occur here if we somehow rearrange. We can't move the methyl group, so a methyl shift isn't possible, but we can move a hydride. So this hydride can move here, which will shift the positive charge to this tertiary carbon, right? And in that case, right, we're going to have this intermediate, right? Because now this has the hydrogen and this has the positive charge. So this is the more stable carbocation. And obviously the possibility for rearrangement will also drive this towards basically a Sn1 or E1 mechanism, because you can create this tertiary carbocation, which is very stable. And then a solvolysis reaction is going to occur if it goes through Sn1. Either it's going to go through Sn1 via solvolysis, because we don't have like any other nucleophile, so water, the solvent, is actually going to act as a nucleophile. Or we're going to have an elimination reaction, E1. And here E1 is probably very probable, because you can create like a really substituted double bond, okay? And so what can happen, right, is, the water will act as a base, and there's a couple of options for what it can take, right? Hydrogen here, hydrogen here, hydrogen here, but we want to create the most substituted one. So it's probably going to be this hydrogen, right? So in that case, the Zaitsev product, okay, the Zaitsev product is going to be this, which is very nice and substituted, okay? And remember that even though there is this rearrangement that happens, there is still going to be some molecule like this one that will react as a secondary carbocation. And in that case, right, if think about it, if you react this secondary carbocation with water as a nucleophile, you're just going to eventually get the same molecule back. So the only unique product from that reaction, it would be an elimination variant of it, okay, where this secondary carbocation reacts and maybe this hydrogen is taken, right? And so if the secondary one reacts, we're going to get this molecule, okay, with the methyl group here, okay? Now, it could also create a double bond here, but again, that's going to be less substituted. So this is going to be the more likely product, okay? And then lastly, there can also be a unique unique Sn1 product that could form would be from the rearrangement, where essentially this tertiary carbon would react with water being the nucleophile, okay? Where basically it would bind to it, and then it would need to be deprotonated, because with the solvolysis, after the H2O binds, it's going to have that extra proton. It's going to be positively charged, so it needs to be deprotonated, okay? And then we're still going to have this whole thing. But this would actually basically, like this reaction pathway, if it went through Sn1 after the rearrangement, you would just have basically shifted this alcohol group from this carbon to this carbon, okay? Exchange them, so to speak. But, you know, so this will happen to an appreciable amount, but this is probably going to be the major products, okay? Really these two. So this is really the Sn1 rearrangement product, and this is the E1 rearrangement product, which is also the Zaitsev product because it's the most substituted. Okay, so next we have number 8, and we have a similar looking structure to that of number 7, except the methyl group here is now on this carbon. And again, it's an alcohol, right? It's an alcohol. And again, it looks like there's going to be some sort of acid catalysis. There's hydrochloric acid and it's in water. So polar protic. There's no, there's no base or nucleophile evidence, strong nucleophile or base. So it's going to be water that's going to react at the end of the day. And most likely with the acid catalyst, it's going to protonate the hydroxyl group, and that's going to act as the leaving group, right? It's going to form initially a secondary carbocation here. But notice that in this case, we can actually do a rearrangement. There's no adjacent hydrogen that can perform a hydride shift to produce a tertiary carbocation, but there is a methyl group since this is a quaternary carbon. So we can have a methyl shift, and let's draw that. If we have a methyl shift after the initial leaving group leaves, we're going to first get this secondary carbocation. This is the secondary one. And then we have this methyl group. So this methyl group is going to shift to that place. And we're going to convert the secondary carbocation. We're going to move that positive charge to the tertiary one. Right? And that is good. And then this positively charged tertiary carbocation, this is now going to react through both E1 and Sn1. All right. And water is going to be the nucleophile / base. So if we do E1, there's going to be a hydrogen here, a hydrogen here, hydrogen here. We want the most substituted alkene, so it's going to involve this hydrogen being taken. So we're going to get the major product for E1, okay, where the double bond is going to be right here. And you could also get some of the other products where these hydrogens are taken. You can try to practice drawing those. However, you will probably still have a substantial amount of Sn1 where water acts as a nucleophile. And so that one is going to look like this, right? You're going to have the water attacks this tertiary carbocation, and then it itself is deprotonated. And so you're going to have a hydroxyl group on that carbon. Right? So there's a hydroxyl group right there. So this is Sn1, and this is E1, and it's the Zaitsev product because it's the most substituted one. So again, kind of like in this previous reaction, we've moved actually the alcohol from one carbon to another through the Sn1 pathway. Now, number 9, we have another ring, and we have bromine as the leaving group, it seems like. And we're reacting in an acetone, which is polar aprotic, so that suits Sn2 and E2. and with this molecule called sodium butoxide. So this is basically a pretty bulky base that looks like this, something like that. Okay, it's pretty bulky, and because it's so bulky, there's a lot of steric hindrance. So it's probably going to act more like a base, but it is also nucleophilic because it has a full negative charge. All right, and this is going to be a secondary carbon. Okay, now given that it's polar aprotic and it's a strong base / nucleophile, this is probably going to go Sn2 / E2. And because the base is so sterically hindered, it's not really going to act very much like a nucleophile, most likely. It's much easier for it to come in and take one of these adjacent hydrogens. But here we got to be careful, because remember that for E2 to occur, you need to have the hydrogen and the leaving group in the anti-periplanar position, right? So if we actually look at the positioning of these hydrogens relative to this bromine, this bromine and this hydrogen are both going out away from us into the whiteboard, right? So if we drew it from the side, this would kind of look like the bromine here, for example, and then hydrogen down here. So they're on the same side. And that's going to be hard for the base to come in and take the hydrogen because there's going to be more steric hindrance. So we want them to be anti-periplanar, where they're opposite each other. And that's nice because here on this side, this hydrogen is actually going the opposite direction as the bromine. So the reaction is going to occur with this specific hydrogen, all right? So when we do the E2 here, right, we're going to have this form. And then I guess we'll keep the stereochemistry to emphasize that here. Now, of course, this isn't, this is a symmetric molecule, so these aren't chiral centers in any case. But, well, excuse me, they are chiral centers, but the main point is that even if the double bond formed here somehow, right, then the molecule would look the same at the end of the day, all right? Unless, of course, the stereochemistry of this particular position is different from this one. I'm not going to really do that in my head right now, but symmetrically, it would look like the same molecule in any case, all right? But the point being, right, the teaching point here is that the hydrogen is going to be the one anti-periplanar to the bromine, all right? So this would be the E2 product, all right? Now, theoretically, it could, despite the steric hindrance, also knock off this bromine via Sn2, okay? And, that would be a much more minor product given the way this base looks because it's so sterically hindered. But you could have a little bit of that, so we can just draw it, right? And remember, since it is Sn2, there's going to be inversion of stereochemistry. So this bromine is knocked out, and you're going to have this alkoxide attached to it now. Right, so there's inversion of stereochemistry here. It goes like that, okay? And then, there's the methyl group. Well, there's the hydrogen, and then the methyl group here, and then the hydrogen here, and the methyl group here, okay? For completion's sake. But most likely, this is going to be the major product, the E2. And again, this is a secondary carbon, and generally when you start having secondary carbons, if you're choosing between E2 and Sn2, E2 is more likely to happen. Speaking of which, we have number 10. And number 10, you can tell right away, it's a polar aprotic solvent, DMSO, favoring E2, Sn2. And then you have this thiomethylate ion with its sodium counterpart. Again, like I said, this is a really strong nucleophile, but it's a really weak base, and we saw that in previous problems. And then we have a chlorine leaving group. Not the best leaving group, but it's still something that can leave the molecule, unlike fluorine, which just can't. And it's a chiral here. And actually, before we even do this reaction, let's just make sure we know what the configuration here is. So the way that I like to do this, by the way, with the configuration is if the highest value group is actually being drawn to be going away from me in the page, I like to imagine that it's actually coming out at me, right? And the hydrogen is going away from me, right? And then in that case, we can then number everything. So this is 1, this is 2, this is 3. And so it goes counterclockwise. So that's S. But then we have to remember that we switched the configuration in our head. So then we switched the one that we got. So if it was S, it's actually R. So this is actually R, right? So then we'll do the reaction. So this is clearly going to go the Sn2 pathway because this is a very strong nucleophile, a terrible base. So that doesn't favor E2. And then DMSO just favors Sn2 and E2 in general. And it is secondary, but again, because this is a really good nucleophile and a poor base, then even the secondary carbon will react really well, Sn2. So the product we're only going to get one. The chlorine leaves, and at the same time, this thiomethylate group, thiomethylate anion, attacks from the back. There's inversion of stereochemistry. So we're going to have the thiomethylate attached, and this is now going to be S, right? And we can see because this is going to be labeled 1, this is 2, this is 3, so it's S, all right? And then lastly, we have this cool looking molecule. We got 2 benzene rings and then an iodine leaving group, great leaving group, and it's in water. So clearly some solvolysis, and look, this is going to definitely produce a carbocation because even though this is a secondary carbon, it's attached to 2 extremely good electron donating groups. It's a crazy high inductive effect. So this will very readily form the carbocation, right? We'll draw it. I like drawing these. This is going to be the carbocation. The iodine has left. It's solvated and stabilized by the water. And then the water, right, the water molecule, it's going to attack, and it itself is going to be deprotonated by another water molecule, and you're going to get the final product, which is basically an alcohol, okay? OH, okay? Now you might ask yourself, it's proceeding through this intermediate, so why not E1, right? Well, the issue here is if you look at these 2 carbons, there's no adjacent hydrogens actually to the carbocation because these carbons are part of these benzene rings and then they're also attached to that carbon. So they already have 4 bonds. They don't have any hydrogens. So this can actually only proceed through Sn1. Really nice. And remember, so basically like even a primary carbon, if it has enough electron donating groups next to it, like if it had a benzene ring or maybe like an allylic group, like an adjacent double bond, carbon-carbon double bond, even that could potentially form a carbocation because these are really good electron donating groups. They stabilize this positive charge really well. And that's it for our example video. Check out our website at mcatsimplified.com.